Hello guys, welcome to our chemistry discussions. Today we are going to have a discussion on the November 2023 paper, chemistry, paper 3. So this is advanced level, A-level chemistry. So we have begun our massive topical revisions in preparation for the exams. So if you are doing Cambridge or any other examples, you need to engage in our discussions. Here we don't stick to examples, but we try to have many questions from different examples so that we can broaden our foundation, we can broaden our understanding in the principles of chemistry. So if you're doing Zimsec, you need to understand these instructions to candidates. So in this paper, you are required to answer 6 questions, and then you are required to answer 2 from section A, which is the physical section, and then 1 from section B, which is the inorganic, and then 2 from the section C, which is the organic, and then lastly we have section D, the options, right? So we are now diving into the first part of the question, and I hope you guys have done this paper already before watching this video, so that you can make use of this session to assess yourself, right? So for section A, number 1 says the isotopes of copper and their relative abundance is shown. The isotopes of copper and their relative abundance is shown in the table. So we've got the first isotope with isotopic mass of 68, and then the next isotope with the isotopic mass of 64, and then we are given this abundance, right? So the first part requires us to define the term relative isotopic mass. So here we don't mainly stick to the given question, but we try to expand the questions in relation to any of the concept within that given radius, so that we can broaden our foundation. We can have an understanding in our multiple choice paper, our structured paper, our free response, even the practical paper, right? So we need to define the term isotope. So isotopes, these are defined as atoms of the same element with the same number of protons, same number of electrons, but different number of neutrons. So these subatomic particles, you've got the same protons, same electrons, but different number of neutrons, meaning to say different mass numbers. So the mass number is made up of the proton plus the neutron. So if we are having different number of neutrons, it simply means that we are going to have different mass numbers. So isotopes, you've got the same proton, same number of electrons, same number of protons, but different number of neutrons. You need to take note of that one, and also you should be able to define the term allotrope. So allotropes are defined as atoms of the same element with different arrangement in the lattice structure. Same element but different arrangement in the lattice structure. So that's the definition for allotropes. So examples of allotropes, we've got carbon and graphite. These are more common examples of allotropes. We also have oxygen and ozone. You need to take note of that one, right? So we have got graphene, we've got Buckminster fluorescence. These are other examples of allotropes for carbon, but graphite and carbon are the more common ones, right? So you need to know the difference between the uses of graphite and carbon, graphite and diamond, right? You need to know the uses between graphite and diamond, because the different in arrangement of particles will result in different physical properties, thereby having different physical properties. Since physical properties are governed by the arrangement of particles, what we call the lattice structure. So diamond exhibits a giant molecular lattice structure whereby the bonds are held by the strong covalent bonds, and then graphite exhibits a hexagonal two-dimensional lattice structure which is layered, and we've got sp2 hybridized orbitals in graphite, and then sp3 in diamond. So you need to take note of the differences between graphite and diamond, right? So here we are given abundance, which is defined as the percentage occurrence of the isotope in the natural occurring element, right? So you should know the definition of each and every term within that topic, right? So we are given abundance and isotopic mass. So we are required to define the term relative atomic mass. So atomic mass, relative atomic mass, relative isotopic mass is defined as the average mass of an isotope of an element measured relative to 1/12 mass of a carbon 12 atom, right? The average mass of an isotope measured relative to 1/12 mass of a carbon 12 atom, right? So you should know the definition of relative atomic mass, relative isotopic mass, relative formula mass, relative molecular mass, the more the Avogadro's law, right? So you should know the difference between relative formula mass and relative molecular mass. So you should know the difference. Here we're using formula units. So using formula units, and then here we're using molecules, right? So this one is for covalent compounds, and then this one is for ionic compounds. So you should know the difference between the two. A relative formula mass is defined as the average mass of the formula units found in a ionic compound measured relative to 1/12 mass of a carbon 12 atom. And then relative molecular mass is defined as the average mass of a molecule measured relative to 1/12 mass of a carbon 12 atom. So that is the definition you need to be aware of, right? And then we're now moving on to the next part, which says calculate the relative atomic mass of copper. So we use the formula. So AR is equal to isotopic mass multiplied by abundance plus isotopic mass of the next isotope multiplied by abundance. So this is the formula over total abundance. So we are simply going to the given information. So the isotopic mass here is 68 and the abundance is equal to 7. So abundance can be in the form of percentage. So you need to take note of that one, right? And then we are given 65 and 3. So it's 65 by 3 over total abundance, which is equal to 10. 7 by plus 3. So we're going straight to our calculator. So it's 68 by 7 to give us 476, and then 65 by 3 to give us 195 all over 10. So it's 476 plus 195 divided by 10. So we're going to have 67.1. So this is the relative atomic mass, right? So you should also explain how the mass spectrometer works. So it is one of the most frequently examined questions. Describe how a mass spectrometer works, right? So you should know how the mass spectrometer works. And then the next part says define. Let me clear this one. So we are required to define the term lattice enthalpy. So it can be also called lattice energy, right? So lattice enthalpy is defined as the energy released or the energy evolved when one mole of a solid ionic compound is formed from its gaseous ions under standard conditions, right? So it is the energy evolved when one mole of a solid ionic compound is formed from its gaseous ions and under standard conditions. So you should also state the standard conditions of 1 atm and a temperature of 298 kelvins. So these are the standard conditions. So here in the definition, you need to take note of this solid ionic compound. So we are going to form a solid ionic compound, right? One more. Also take note of this one more. These are the key terms you need to take note of when describing the standard enthalpy change of lattice energy, right? So it is the heat evolved, not the heat change. So meaning to say it is always exothermic. It is always exothermic, right? So we're going to move on to the next part of the question, which says state and explain state and explain two factors that affect the magnitude of lattice enthalpy. So lattice enthalpy, from the definition, we understand that it is the energy released, meaning to say it is always exothermic when one mole of a solid ionic compound, so meaning to say we are having a positively charged ion, which is the cation, and the negatively charged ion, which is the anion. So the energy released when these two bond, it is what we call the lattice energy or lattice enthalpy. So the smaller, so it is governed by two factors: ionic size and ionic charge. So the smaller the ions, the bigger the electrostatic force of attraction between the ions, and then the bigger the charges, the bigger the electrostatic force of attraction between the particles, thereby leading to a stronger or a larger magnitude of enthalpy, right? So you can say that smaller ions allow closer approach, thereby enhancing. So that's enhancing the electrostatic forces of attraction between the particles or between the ions, thereby resulting in a larger magnitude of lattice enthalpy, right? And then we can also say that the higher the charges or the bigger the charges, the stronger the lattice enthalpy, or the bigger the magnitude of lattice enthalpy. So higher charges on the ions, increases the strength, to increase the strength of the electrostatic forces of attraction between the oppositely charged ions, thereby increasing the magnitude of lattice energy or lattice enthalpy, right? So we're now moving on to the next part, which says explain why the enthalpy change of hydration of magnesium is equal to 1927, whilst that one of sodium is equal to 406. So enthalpy change of hydration is always negative, meaning to say it is always an exothermic reaction. It is being evolved. So it is defined as the heat evolved when one mole of a gaseous ion completely dissolve in water to form an infinitely dilute solution under standard conditions of 1 atm and 298 kelvins. So we are having magnesium having a higher enthalpy of hydration, and then sodium ion having a lower. So enthalpy change of hydration is governed by what we call the charge density. So charge density, we are saying that we are having this magnesium ion with a smaller radii than the sodium ion. So across the period ionic radii decreases. So again, you have this for inorganic. So this one is for anions, and this one is for cations, right? So across the period we are having this sodium ion, and then this one magnesium ion. So the smaller the ion, the bigger the effective nuclear charge on the exterior environment, right? So effective nuclear charge is more experienced on these magnesium ions compared to this sodium ion. And then we are having a charge of +2, and then you are having a charge of +1, meaning to say we are going to have strong attractions here than here. So this +1 singly charged ion is being distributed over a larger region, and then this +2 is being distributed over a smaller region, meaning to say it is more experienced in this exterior exterior environment. And then from the definition, we are having water molecules. So water molecules are negatively, has got a negative region. So this is our oxygen, and then this one is our hydrogen. And then water has got the oxygen atom has got 2 lone pairs. So these magnesium ions will have a strong attraction to this negative electron center, the electron region, than this sodium ion. So the attractions here are smaller compared to the attractions of this magnesium ion. Why? Because of this charge density ratio, because of the smaller ionic size. So we can explain our answer saying that the more the negative value of magnesium ion compared to that one of sodium is due to the high charge density, right? High charge density of magnesium ion. You have a smaller ionic radius, right, than the sodium ion. So the ionic radius of magnesium is smaller than that one of sodium, and we also have a higher charge of +2 on magnesium, and then +1 on sodium. So the charge density of magnesium, the charge density of magnesium is higher than sodium ion. So this will result in the stronger ion to dipole interactions with the water molecule, right? With the water molecule, thereby releasing more energy, right? So this is the explanation why the enthalpy change of hydration is larger for magnesium than that one of sodium, because of charge density ratio, which will then allow the strong ion dipole moments or ion dipole interaction between the water molecules and the magnesium ion. So I hope this is clear, and we are now moving on to the next part. So the next part of the question says, state 2 conditions for the formation of hydrogen bonding. So hydrogen bonding, we are having hydrogen bonded directly to one of the most electronegative atoms, which possesses a lone pair of electrons. So hydrogen must be bonded directly to one of the most electronegativity atoms. Must be bonded directly, and then the electronegative atom, must have at least one lone pair of electrons. So examples for these atoms, we are going to have a fluorine, nitrogen, and then oxygen, right? So these are the electronegative atoms, right? And then we are moving on to the next part. So the next part says, sketch a PV against P on the XM axis to show the following gases, how they deviate from ideal behavior. So you've got ammonia, carbon dioxide, and then helium. So let me add another page so that we can control the graph clearly, right? So it's PV. So this is my PV against P. So this is my horizontal axis. And then here we are having the ideal gas. So this one is the ideal gas. And then noble gases, they deviate slightly from ideal behavior. So here is my helium. Right, so let me rub. Must deviate slightly. So this is my helium. And then carbon dioxide will deviate. Right, and then ammonia will deviate mostly from ideal behavior. So here we are having ammonia, and then here we are having carbon dioxide, and then here helium. So here is the ideal gas behavior. So this is the graph PV against P. We're moving on to the next part, which says explain the difference in the graph. So helium doesn't deviate as much as other gases from the ideality because it is a noble gas. So noble gases exist as mono atomic particles, right? So the forces or the van der Waals forces between the particles are weak as compared to other compounds. So for every noble gases, the group 8 elements, the noble gases, they exhibit a simple molecular lattice structure where the monoatomic particles are held by the weak van der Waals forces. So the monoatomic particles are held by the weak van der Waals forces. And then we move on to carbon dioxide, which exhibits a simple lattice structure, simple molecular lattice structure, where the particles are held by the stronger. So here we've got stronger van der Waals forces compared to that one of helium. For helium we've got weak, and then here we've got stronger van der Waals forces, thereby increasing the strength of the lattice structure. So this will cause the molecule to deviate more from ideality nature, right? So carbon dioxide will deviate more from ideality. And then in ammonia, right? So in ammonia, hydrogen is bonded directly to one of the more electronegative atom. So this one we are going to have hydrogen bonding. So here we've got van der Waals forces, and then here we are going to have the hydrogen bonding. So hydrogen bonding is the strongest, one of the strongest intermolecular forces. So thereby increasing the strength within the lattice structure of the molecule, thereby causing the molecule to deviate much from ideality. So we can say that in helium, so there is a simple molecular lattice structure whereby the monoatomic particles are held by the weak van der Waals forces. And then for carbon dioxide, the van der Waals same lattice structure, simple molecular lattice structure whereby the particles are held by the weak van der Waals forces. But the van der Waals forces in carbon dioxide are much stronger than those in the small monoatomic particles in the helium. So you have got weak van der Waals forces, and then you have got stronger van der Waals forces, causing carbon dioxide to deviate more from behavior. And then for ammonia, we have a simple molecular lattice structure but with different forces. Here we've got hydrogen bonds as the intermolecular forces, thereby increasing the strength of the molecule, thereby causing it to deviate much from ideal behavior. So that is what you need to know for your explanation. So we are now moving on to the next part of the question, which is number 2.